Now let's have a closer look at how all of this is implemented within the channel emulator, simply called CELEOS. And let me assure you, this is the channel emulator you are looking for. How does CELEOS work? The general idea behind the architecture of the channel emulator is use a software-defined radio to perform analog to digital and digital to analog conversion of RF signals and off-the-shelf GPUs for processing. The signal is designed to be hardware agnostic, being able to function with a range of both SDRs and GPUs. Several configurations can be implemented, varying in terms of hardware, and therefore in the number of supported channels and their bandwidth, but all using the same software. The structure of the proposed SDR-based satellite radio channel emulator is described in the high-level block diagram. The main components of the channel emulator are channel emulator hardware device, software-defined radio module and a host computer, signal processing software, which is software modules to be included in the SDR and host computer to emulate all the signal impairments in real satellite radio channel, and the graphical user interface application, which allows users to operate the channel emulator and to select the appropriate satellite channel or apply individual parameters. Although the structure here is exemplifying 2 pairs of RX-TX ports, the tool itself is not limited to this number. The limitation only comes from the used hardware. CELEOS starts from a realistic satellite motion model. By importing TLE data, we accurately track satellite position over time. This defines the satellite's absolute coordinates at each time step, enabling computation of trajectory-dependent channel effects like delay, Doppler, and distance-based attenuation. The dynamic nature of this tracking allows CELEOS to reproduce time-evolving conditions that match what a real NTN terminal would experience. CELEOS, henceforth, offers 2 ways to model satellite orbits. The user can choose a generic orbit type, LEO, MEO, or GEO, which automatically applies standard orbital parameters for that class, or alternatively, the user can load a custom TLE file which contains precise 2-line orbital elements. Once imported, CELEOS computes the satellite's real-time position, trajectory, and all channel-dependent parameters for emulation. This flexibility supports both fast setup and high-fidelity satellite-specific modeling. Propagation delay changes as the satellite moves. CELEOS models this by splitting delay into constant part and a dynamic part. The constant delay is applied through a basic buffer. The variable delay is implemented using fractional resampling per signal buffer, allowing precise delay changes over time to simulate satellite movement in a realistic and granular way. One concern with SDR-based emulation is added system latency. We measured this within the full chain, from SDR input through host processing to SDR output, and confirmed it stays below the minimum delay for even the closest LEO satellite pass. This ensures that CELEOS remains accurate for real-time use and the emulation remains valid and consistent for real-time testing. 2 milliseconds to 1,000 milliseconds, which is supporting LEO, MEO, GEO, and beyond, and down to 1.5 milliseconds for lower bandwidths, but this applied to bandwidth below 40 megahertz. Weather conditions, especially rain, have a significant impact on signal quality at satellite frequencies. CELEOS includes pre-modeled scenarios for weather conditions such as clear sky, moderate rain, or intense rain. These are based on statistical propagation model and can be toggled in the user interface to simulate real-world link degradation under various weather conditions. Power loss due to atmospheric conditions based on ITU are P618-13, whereas rain rate calculation are based on ITU are P837. CELEOS can degrade the signal using wide Gaussian noise to emulate different SNR values. Wide Gaussian noise can be added digitally via live random number generation, while to simulate interference, we inject either a pre-recorded 5G signal or DVB-S2 signal. This can be done by using pre-recorded signals via SIGMF. Depending on the propagation path, the values can be set only for uplink or both for uplink and downlink. These are uncorrelated with the main waveform and scaled to hit a target SINR, making it possible to test receiver robustness in hostile air-off conditions. As the satellite moves relatively to the ground station, a Doppler shift is introduced. CELEOS calculates this in real time using TLE satellite trajectory and user-defined ground station movement. The result is applied to the signal using a complex exponential, effectively simulating the frequency shift experienced in orbit. Doppler shift implementation in the channel emulator is done multiplying the signal with a complex exponential highlighted here, where Ft is the desired Doppler shift. Note that the Doppler shift should be computed for the actual channel frequency, even if the signal is baseband processed in the SDR-based emulator. In the previous slides, simulation for Doppler effect for the Starlink satellite has been exemplified, having, as mentioned, the central frequency of 5 GHz. This is plotted in the shown figure here. CELEOS features as well a user-friendly interface. In simple mode, you can choose your satellite type and operating band. The system automatically applies all relevant impairments for that scenario, making this mode perfect for quick tests and demonstrations. Nevertheless, there is also an advanced profile. In this advanced mode, CELEOS provides fine-grained controls. You can load TLE files, select a specific satellite, and configure parameters like noise, interference, amplifier nonlinearity, and weather conditions. These settings can be stored as channel profiles for future reuse, ensuring consistency across test campaigns. There are also some extra functionalities within CELEOS. CELEOS supports Diffie standard, which enables seamless integration and interoperability between various satellite communication systems. By incorporating Diffie functionality, the emulator ensures compatibility with multiple platforms, simplifying the exchange of information and facilitating communication across different systems. This ensures as well that CELEOS can be used as a Diffie generator, but more than this, as a Diffie to RF and RF to Diffie converter. While emulation is running, users can monitor the spectral input and output of the channel using the integrated spectrum analyzer. This feature mirrors the functionality of a physical spectrum analyzer, offering comparable usability and options with additional compatibilities currently in development. To validate CELEOS, we tested it in a full 5G NTN setup. A satellite channel was emulated between an SDR-based GN, G-Node B, and user equipment. The test confirmed CELEOS's ability to accurately reflect link impairments while supporting real-world 5G operations end-to-end. CELEOS proves that satellite channel emulation doesn't require expensive hardware. Unlike bulky, hardware-locked testbeds, CELEOS is entirely software-defined, lightweight, highly flexible, and delivers the timing, attenuation, and mobility models needed for realistic NTN testing, whether in the lab or in live 5G NTN-based systems. CELEOS brings the fidelity and precision needed for serious NTN development. Henceforth, CELEOS is more than just an emulator. CELEOS is a complete ecosystem for developing, testing, and validating 5G NTN solutions, and it is basically an emulator, a DIFI to RF, RF to DIFI converter, DIFI generator, digital spectrum analyzer, and it also comes with a DIFI API add-on, which can be integrated in other products in need of DIFI. So, if you are working on NTN or planning to start working on NTN, try the leading software-based NTN channel emulator. Try CELEOS today. So, I hope this session has shown you that realistic, scalable satellite channel emulation doesn't need expensive hardware or rigid setups. With CELEOS, you have a flexible, software-defined platform that's purpose-built for the demands of your 5G NTN journey. That being said, stay tuned for more sessions and product updates from Lasting Software. And if you have any questions or feedback, we'd love to hear from you. Thank you for your time and attention. Until next time, bye.